Now I am moving into the second example. In this example, I have taken the barber shop example which I have discussed in the model 1 also, the same example. So, the owner of a local one chair barber shop is thinking of expanding the shop capacity because there seems to be too many people are turned away. Observation indicate that in the time required to cut one person's hair, there may be 0, 1 and 2 arrivals with the probability 0.3, 0.4 and 0.3 respectively. So, this information is very important. That means during one person's haircut, what is the probability that no people turned up with the probability 0.3 and 1 people may turned up with the probability 0.4, and there is a possibility 2 arrivals is possible during the one person's haircut with the probability 0.3. Therefore, the summation of probability is going to be 1. So, during the one person's haircut, these are all the only 3 possibilities are possible with the 0 arrival or 1 arrival or 2 arrival. The shop has a fixed capacity of 6 people, including the one whose hair is being cut. That means maximum 6 people can be allowed in the system. So, 5 people can wait maximum and 1 people under the service. Any new arrival who finds 6 people in the barber shop is denied entry. That is the meaning of capacity of the system is finite with the size 6. Now, I am going to define the random variable. Let x n be the number of people in the shop at the completion of the nth person's haircut. This is very different random variable, or this is very different stochastic process. Usually the parameter space is time, but here the parameter space is the number of people in the shop. The n is the parameter space is the person who leaves after the haircut. So, it's a nth person who leaves the system, that becomes the parameter space, whereas the random variable is how many people in the system when the nth person leave the system. That means, you should not count that person when you are finding the values of x n. That means, this number is counted at the departure time point. So, when the nth person leaves, how many people in the system, and the system is maximum 6 people allowed. Therefore, he cannot see more than 5 people in the system when he leaves. So, because of this constraint, because of during the one person's arrival, either 0 or 1 or 2 arrivals can take place and so on. Based on this information, the stochastic process x n is going to be a discrete time, discrete state stochastic process, as well as the Markov property satisfied. That means, the probability of x n plus 1 take some value, given that all the previous values are known, that is same as the conditional probability distribution of x n plus 1 takes some value, given that x n was some value. So, the future distribution, given that present as well as the past information, is same as the future distribution given the present, not the whole past information. So, this Markov properties will be satisfied by this stochastic process. Therefore, this x n will form a discrete time Markov chain. Obviously, it is the time homogeneous discrete time Markov chain also. So, in this example, our interest is to find out what is the one step transition probability matrix. This is going to be the one step transition probability matrix, and the possible states S is going to be 0, 1, 2, 3, 4 or 5, because the capacity of the system is 6, and whenever the nth person leaves, either first person, second person, third person leaves, how many people are in the system? Therefore, the maximum will be 5, and there is a possibility when he leaves no one will in the system also. And this is the one step transition probability matrix, and this is also going to be a square matrix because it is going to be a countably finite number of elements, and this is the 0, 1, 2, 3, 4, 5. Now we can discuss what is the probability that 0, 0 in one step. That is nothing but in the nth, when the nth person leaves, no one in the system. When the n plus 1th person leaves, no one in the system. What is the probability for that? That is x n plus 1 is equal to 0 given that x n was 0. It is a one step transition probability. It is independent of n because it is a time homogeneous. It is a one step transition probability matrix. So, this is possible at some person leaves, whatever be the n, nobody in the system. When the next person leaves, nobody in the system. So, that is possible by when some person leaves, the system was empty for some time, you do not know how much time it was empty. Then the n plus 1th person enter into the system, and during his haircut, no one turned up, or no arrival takes place during his or n plus 1th haircut is going on. Therefore, when he leaves, no one in the system. So, we are not bothering when he enter into the system and so on. Our interest is how many numbers of people in the system when the n plus 1th person leaves, and this probability is n plus 1th person leaves, 0 people in the system, and given that when the nth person leaves also 0 person in the system. So, that is possible with the explanation I have given. No one enter into the system during the n plus 1th person's haircut, and the information is provided indicate that the time required to haircut one person haircut, there may be a 0, 1 or 2 arrivals with the probability 0.3. So, no arrival takes place during the one person's haircut is a 0.3. Therefore, this probability is possible with the probability 0.3. Whereas, P 0 1 of one step, the same way you can write probability that x n plus 1 is equal to 1 given that x n is equal to 0. That is possible when the nth person leaves, no one in the system. When the n plus 1th person leaves, one person in the system, that means during his haircut, one person enter into the system. That is possible with the probability 0.4. Similarly, from 0 to 2 in one step, that is going to be 0.3 with the probability 2 arrival takes place during the n plus 1th person's haircut. Now, the second row. Second row, what is the probability that when nth person leaves, one person in the system, when n plus 1th person leaves, 0 person in the system. That is possible during the n plus 1th person haircut, there is no one in the system, no arrival takes place, therefore, that probability is 0.3. And from 1 to 1, that is possible with one person arrived during the n plus 1th person haircut, therefore, that probability is 0.4. And going from the state 1 to 2, that is possible 2 persons arrived during the n plus 1th person haircut. Whereas, from 2 to 0, that is not possible, because when nth person leaves, the 2 person in the system, therefore, n plus 1th person in the leaves, definitely he will see one person in the system, because of no arrival and 1 arrival and 2 arrival. Therefore, it will be shifted by one column and it will be keep continuing till the end. Whereas, the last one, what is the probability that the 5 people in the system when the nth person leave, and 4 people in the system when the n plus 1th person leave, that is same as no arrival takes place during the n plus 1th arrival, n plus 1th haircut going on. So, therefore, this is going to be 0.3, whereas P 5 to 5 in one step, that is possible with the combination of one person arrive the system or 2 person arrive the system. This system size is going to be maximum 6. Therefore, when n plus 1th person haircut is going on, if one person arrives, then he will be entered. If 2 person arrives, then he cannot be accommodated. Therefore, he won't join the system. Therefore, the system, the number of customers in the system in the x n, that is going to take the value 5, and the combination of 0.4 as well as 0.5. Therefore, this probability of system is moving from 5 to 5 is 0.7 because of 0.4 plus 0.3. Now, I can give the state transition diagram for this example, because S is going to be 0, 1, 2, 3, 4, 5. Therefore, the nodes are going to be 0, 1, 2, 3, 4 and 5, and the possible values from the from the one step transition probability matrix I can make out. So, 0 to 0, that probability is 0.3, and 0 to 1 is 0.4, and 0 to 2 is 0.3. Similarly, I can fill up the all other things, and 5 to 5, that is very important, and 5 to 4, that is possible with the probability 0.3, and 5 to 5 is possible with the probability 0.7. So, this is the state transition diagram. I did not complete the state transition diagram. We have to fill up all the arcs with the weights going from one arc to other arc with the positive probability. Wherever there is a probability 0, we should not draw the arc for it. So, in this lecture, we have discussed the discrete time Markov chain, then we have given the few important properties, followed by we have explained the one step transition probability matrix, and also we have given 2 simple examples. With this, the lecture 1 is over for the module 4. Thanks.